Ooh.
Yeah. Just this way, people won't be wondering what they missed.
Hello, everyone. Is this working? Hello. Good morning, friends. Real quick, if we could just snag your attention for like 1 minute max. My name is Maddie. That's my pal Curtis. We're with a student org on campus called GIVE. We're having information sessions all day tomorrow, so that's going to be that green flyer. Take one down, pass it around. So what we do, we mix really meaningful volunteer work, working alongside local communities, empowering them to build critical infrastructure, sustainable development, farming, as well as wildlife conservation and increasing access to education. And then our motto is work hard, play hard. So you could sandboard down an active volcano in Nicaragua, dive with wild dolphins in Tanzania, trek to Everest Base Camp, summit Mount Kilimanjaro, you name it, the list goes on. So if any or all of what I just said interests you, come check us out tomorrow. You could come as late as you want, leave as early as you want, whatever works for your schedule. But yeah, I hope to see some of you guys tomorrow. Just a little bit of advice. I didn't ignore that green flyer 3 years ago, and I've been to the most beautiful countries, so is Curtis, working alongside the most beautiful local communities. So come hang out with us tomorrow, but thank you guys for your time. Thank you.
Okay, so I'm going to get started. Hopefully you guys had a great long weekend. If you're sitting up in the back, it looks like there's a handful of seats scattered throughout the room. Okay, so if you're just joining us now, I guess the first lecture I went over kind of the syllabus and how the classes run, but the website that we're using is orgchemboulder.com. If you go there, there's a link to the lecture page. If you're taking lab, all the lab stuff's on there too. But if you go here, you can get the syllabus for this class, and you can also get a hold of the typed lecture notes, which is what I generally lecture off of, and also lecture capture videos for the first 3 classes, plus for the entire rest of the semester as we go on. So even if you missed a whole bunch of stuff last week, not to worry, you can catch up. Okay, so any questions about that? Oh, one other reminder, I guess. So recitations, we did not have the first week or the second week, but they will start next week. So the first meeting with your recitation TA will be Monday and Tuesday next week. Okay. So picking up where I left off last week, we got up through Lewis dot structures. And so now we're going to spend a little while looking at some more detailed pictures of basic molecules. So today we're going to start in on molecular structure. Okay, so really there's two parts to structure. One of these is connectivity. So what connects to what, obviously from the name. And we know from looking at covalent versus ionic bonds last time that covalent bonds, connectivity is actually very important and well-defined. Unlike ionic, where it's just sort of a bunch of ions in the same general area as each other, connectivity means that covalent bonds link specifically two atoms to each other. So the other part of it is geometry. Which more looks at how are the atoms arranged in space. Okay, so there's a few different parts to geometry, but the two main ones that we're going to be dealing with are bond lengths and bond angles. There's actually a third part that we're going to look at right at the end, but we'll spend a while longer on that in Chapter 2. Okay. So say we're looking at methane again, CH4, which I'm going to draw like this for the time being, but we'll cover why that's not fully accurate in a bit here. Bond length would be like, what is the distance from the center of the carbon atom to the center of a hydrogen atom? And bond angle would be, if you've got three atoms, say HCH, what is going to be the angle between those two bonds? Okay, so geometry is going to be looking at both of those things. Let's look at bond length first because that's a little simpler. So all else being equal, when we're looking at bond length, shorter bonds are stronger bonds. And the reason for that is that we know that we have to share 2 electrons between atoms, and it turns out you get better sharing, I guess is one way to describe it, the closer the atoms get together. That runs up against some limits once they get too close, but at least for standard covalent bond distances, shorter is stronger. Okay, so bond length, it turns out, follows 3 main trends or rules. So first is, actually I'm going to go down over here. As you move down the periodic table, bonds get longer because the atoms are bigger. So again, all else being equal, if we just swap one atom out for something a little further down the periodic table, then the bonds are going to get longer. Okay, so I'm going to throw up some examples here. So if we try water versus the equivalent using the next atom below oxygen, sulfur, so H2S, hydrogen sulfide, versus the one below that, hydrogen selenide, which is the next one down, we can look at what is the length of the OH versus the SH versus the SEH bond. So this is going to be in angstroms, 0.958, 1.346, and 1.46. So the exact numbers are not super important and you don't have to memorize them, but just to sort of see what trends we're looking at and how big an effect it has. It's a pretty big gap. It's about a factor of 1.5 just by going 2 spaces down in the periodic table. Okay, the second one that we're going to see is bond order. As bond order increases, bonds get shorter. So the most convenient series of molecules to look at increasing bond order is actually the same ones I used for covalent bonds for Lewis dot diagrams last time. So carbon with either a single bond and enough H's to round it out, or carbon with a double bond and enough H's, or carbons with a triple bond and enough H's. Okay, so these bond lengths, the carbon-carbon bond in each molecule, ranges from 1.536 to 1.330 to 1.203. Okay, so again, pretty sizable trend, not quite as noticeable, not quite as strong an effect as moving around in the periodic table, but still fairly powerful. And that's not too surprising, right? Like having more bond order between 2 atoms means there's more electrons shared, which means that probably the bond is going to be stronger, which means that it's going to be correspondingly shorter. Okay, so the third one is moving sideways on the periodic table. So moving right in the periodic table, bonds get shorter, but it's only a little bit. And this is for a similar reason to trend number 1. It's because the atom size changes just slightly as you go across the row, but it's not as big an effect as straight up moving downwards. So for that, I'm going to use second row of the periodic table, so either carbon with an H and then some extra H's to round it out, or nitrogen with an H, or oxygen with an H. Okay, so these numbers are going to be just about the same, but slightly different. So this one's 1.091. Sorry, that's kind of in the shade of the board there. I'm going to write it down below, actually, just so everyone can see. 1.091, 1.008, and 0.958 angstroms. Okay, so kind of a tiny effect on that one, but it does sometimes still matter. Okay, so any questions about those 3? Okay, cool. So that's pretty much all we're really going to cover in terms of bond length. It turns out to be not super important for a lot of things that we're going to look at, although it will pop up from time to time, so it's good to have a feel for how these trends work. What turns out to be much more relevant to a lot of things that we're going to do is bond angles. So bond angles are determined by a model called valence shell electron pair repulsion. Which goes by something that looks like it should be pronounced Vesper, but is actually for some reason pronounced Vesper. Okay, so the name kind of tells you what's going on here. If you've got electrons in the valence shell of an atom, they're going to repel each other. They're going to feel repulsion from each other. And they're going to spread out into sort of the most evenly distributed geometric arrangement that they can get. So okay, so which shape you get depends on how many electron-rich areas you have around the atom. So you want to count areas of electron density. So either lone pairs or bonds to other atoms, but we're ignoring the bond order. So like a double bond counts the same as a single bond. It's still just one region of electron density. Okay, so we're ignoring bond order, in other words. Triple bonds count the same as double bonds. Okay, so we can sort of go through this systematically and look at what if we have two regions of electron density. So two groups or two regions of electron density. Those two groups are going to push off each other and try to get as far apart as they can around the central atom. And so they're going to end up pointing completely opposite directions. So we call this geometry linear. And it has a bond angle of 180 degrees. So one example of that might be, all right, so if we're focusing on this carbon atom here, for example, it has two regions of electron density coming off of it. It's got a single bond to this H, so this is one, and it's got a triple bond to this carbon, which we count also as just another region of electron density. So it's got two total. So two groups makes it linear. So that tells us this bond angle is 180 degrees apart. So this carbon is basically a straight line with the H sticking out one side and the carbon sticking out the complete opposite side. Okay, so questions about that example? Okay, cool. Moving the camera. Okay, so we can carry on. What if we've got three groups coming off of a carbon, or off of whatever central atom? So three groups, or areas. Turns out the best way for those three groups to get away from each other and take up the maximum amount of space they can is by spreading out into basically a triangle where they're all flat in the same plane, but they're sort of pointing three different areas, three different directions within that plane where they're making an equilateral triangle. So this is called trigonal planar. And it turns out, because it's a triangle, the angle between the groups on there is 120 degrees. Which makes sense, right? It's like a third of a circle, 360 degrees. Okay, so here's some examples of that. For example, this boron, for reasons that we'll talk about later, has an unfilled octet. It doesn't have any lone pairs. All it's got are the 3 single bonds to H's. So 1, 2, 3. And so those 3 areas of electron density are going to spread out as far as they can. And so we're going to end up with a bond angle between each set of bonds of 120 degrees, or trig planar, as we would normally abbreviate it. Okay, another example using carbon. Here's a carbon with a double bond to this one. So we've got, again, 1, 2, 3 regions of electron density. So this is also going to be trig planar. 120 degrees on that carbon. And that's true. Like, I chose to label just this bond angle, but the other 2 are also 120 as well. It might be just slightly off depending on if the groups are really huge, but usually it's pretty close to 120. Okay. So any questions about those examples? Okay. So for groups, which we know is pretty much the max we can have if we're sticking to the octet rule, because it's 4 electron pairs or 8 electrons. So this is going to be tetrahedral. And it turns out, for reasons that you can sort of go through and calculate if you're good at geometry, but we're not going to look at, the bond angle turns out to be 109.5 degrees. So this is kind of special because the other 2 were capable of being drawn flat in a plane. Like, if I draw it like this on the board, it straight up is accurate because this carbon is flat in the plane, this is flat, this is flat. These ones too, these are flat molecules. It's just a triangle that's all in one plane. Tetrahedral is the first one where we actually have to start thinking in 3D. So we need some way of drawing that. So we need to show this in 3 dimensions. And so this is where we're going to start using some fancy looking bonds. So coming towards you, can either be shown as a wedge or it can be shown as a bold where there's like neither end is thicker than the other. I favor drawing it as a wedge myself because it makes it very clear which end is coming out towards you. Like this, whatever atom is attached up at the top end is supposed to be like poking out towards you, which is why it kind of looks like it's drawn this way. We can also show things that are going away from you, like sort of like they're poking back behind the blackboard here. And these are shown as dashed bonds. So whatever atom is going away from you, you would show at one end of the dashed bond. And ideally, that end that's going away from you would also be wider than the end that's attached to whatever central atom you're looking at. That's a little harder to draw so that it doesn't look messed up, at least on the chalkboard. Okay, so if we're drawing a tetrahedron, we can show it as two atoms in the plane, one atom coming out towards you, and one atom going away from you. All right, so tetrahedron is sort of like a pyramid, but with a triangle as a base instead of like a square as a base, like you would think of for, say, Egyptian pyramids. If you play D&D, this is the shape of a D4 die. Okay, so the bond angle between any two atoms here is 109.5 degrees, and I picked these two, but I could have picked any other pair. So someone last lecture asked a question of, if I'm showing methane flat in the plane like this, or like I did up there as the very first drawing I did today, for example, is there any difference between the two hydrogens that are shown, say, like next to each other versus ones that are on opposite sides? And it turns out that no, because next to each other versus opposite sides isn't really just a distinction that exists. Like these two H's are equally close to each other, 109.5 apart, as these two H's, even though it sort of looks like these two are spread out more just based on the perspective that we're drawing it from. So if you've picked up a model kit yet, if you want to just like take a black carbon atom and plug 4 H's onto it and then just like play around with it a bit, you can sort of practice viewing it where, you know, you've got 2 H's in the plane and one coming towards and one going away from you, but you should see that all 4 of the H's are equivalent to each other spatially. Okay, so questions about that? We're going to spend a whole lot of time this semester drawing stuff in 3D, so there's a couple of labs actually that are sort of designed to get you comfortable with building models and rotating them around and then translating that to paper. Okay, so one more example is our friend BF4- that we spent a little while last lecture or two looking at the electron dot structure of. So this has also got 4 regions of electron density. And I'm just realizing I drew this as the mirror image of the way I have it in the notes, but it doesn't matter. You can draw this a whole bunch of different ways, and they're all still tetrahedra. Okay, so this is all 109.5 degree bond angles as well. They're all equivalent atoms. They're all spaced out equally from each other. Okay. Good question. So the dipole itself, like within the bond, doesn't really affect it, but there is actually something that does tweak it a little bit. So that's actually what I'm about to cover next. Thank you for the segue. Okay, so what if, instead of looking at all of these things that are bonds to other atoms, I mentioned over there that lone pairs also count as groups. So how is that going to look? So what if some of the groups are lone pairs? Turns out we can't really see lone pairs the way that we can see atoms using X-ray crystallography. But we can sort of determine their influence just by the fact that they're still taking up space that the other atoms are sort of squeezed out of. Okay, so here we're going to have to differentiate between electronic geometry. So in other words, just the VSEPR arrangement that we've been looking at so far. Differs from the molecular geometry. Which is basically, we take the VSEPR geometry and we only look at the atoms, not the lone pairs. So I'll show what that looks like in a second here. Okay. So let's look at an example here. Okay, so we remember those handy kind of guidelines from last time. Nitrogen, if it wants to be neutral with a full octet, it's going to need 3 total bonds plus 1 lone pair. So this nitrogen has 3 total bonds, 2 of them to a carbon, 1 to an H, and it's got a lone pair. So we have a total of 3 regions of electron density, 1 for the carbon, 2 for the H, and 3 for this lone pair up top. So we would expect what Vesper geometry here? Yep, trig planar. So, so we got trig planar electronic geometry. Almost. Turns out that lone pairs, because they're not, I guess, anchored down into a covalent bond with another atom, might be one way to think of it. They actually take up more than their fair share of space around the central atom, around the nitrogen. So it takes up a little too much space. And so the bond angles are going to get slightly distorted as a result. So whatever atoms you have bonded to the nitrogen, in this case hydrogen and carbon, are going to be just a little bit closer than 120 degrees. In this case, they're going to be about 19 degrees. And that means that the lone pair to the H is going to be just slightly over 120. Okay, so the electronic geometry is still trigonal planar-ish. The molecular geometry, we can't see the lone pair really. All we can see is that there's a carbon-nitrogen-hydrogen bond that looks like it's 119 degrees. So molecular geometry we're going to describe as bent. Okay, so another example, again, I think I can fit it in down here. Again, featuring the lone pairs on nitrogen. Actually, no. So I'm going to draw this slightly differently than I did in the notes, but again, tetrahedra are the same thing, even if you draw them from a different point of view. Okay, so again, nitrogen has 3 bonds and a lone pair to be stable. Electronic geometry is tetrahedral. But out of that tetrahedra, for one thing, it's not exactly 109.5 anymore. That lone pair is again taking up more than its share of space. And so this is sort of squashing together the rest of the stuff around the nitrogen just a little bit. In this case, it turns out to end up at about 107 degrees. So again, the exact numbers here are not super important. It turns out it's kind of a complicated balance between trying to optimize like getting electrons away from each other as much as they can versus trying to stick to the right electronic geometry. And 107 just happens to be like a local minimum energy-wise once you add everything together. So it's tetrahedral electronic geometry with slightly distorted angles. But the molecular geometry, we can't see the lone pair. All we're seeing is sort of this tripod with like a nitrogen on top and 3 H's sticking out from one side of it. So this one we would describe as trigonal pyramidal. Molecular geometry. Okay, so pretty much we've looked at when there's 3 regions but one of them's a lone pair. We've looked at when there's 4 regions but one of them's a lone pair. Now let's look at 4 regions but 2 of them are lone pairs. I'm actually going to put my lone pairs in the front and back here, kind of like I have in the notes. Okay, so 1 lone pair here, 1 there. This is a water molecule again, by the way. Okay, so again, 4 regions of electron density. We would expect roughly tetrahedral-ish electronic geometry. But we're only seeing 2 parts of that tetrahedra, which, by the way, are even more squeezed together than they were when there was just 1 lone pair. So these ones end up being about 105 degrees. So this we're again going to describe as bent. Okay, so bent is actually kind of an overloaded term. It can apply to tetrahedral geometry, so like 109-ish degrees, or it can apply to trigonal planar geometry, so like 120-ish or slightly under. Basically, it's just saying it's not linear geometry. Okay, so questions about that? Okay, cool. So I sort of mentioned that there was a 3rd part that we're only going to dip into a little bit for now, but the next chapter is going to focus on it a lot more. And that is sort of a fancier version of bond angles. And that is called dihedral angles. Okay, so regular bond angles are just, you're measuring spacing between 3 atoms. So like, for example, over here we measured H to C, which was 180 degrees. Dihedrals, what you're actually measuring is 4 atoms where you can rotate the middle bond. So kind of a really simple example is hydrogen peroxide, which turns out to have a chain with hydrogens on either end and oxygens in the middle. This central bond can rotate freely. So I'm drawing sort of like this little swivelly arrow as it spins around itself in the middle. And so you can have them where the hydrogens are pointing opposite directions like this, or you can have them, where the hydrogens are pointing opposite directions. Or you can have them where the hydrogens are pointing the same direction, or anywhere in between, like you could have one H up and one coming out towards you. So that can freely rotate as well. So we're not actually changing the bond angles, like H to O is still about probably 105-ish, like up here in water. But we still have 1 degree of freedom where we can swivel this part around the middle without changing the lengths or the bond angles. We are just changing the dihedral angle. Okay. So you need 4 atoms in a row to be able to look at these, but most of the molecules that we're going to be seeing in organic are way more than 4 atoms. So this is actually going to become quite relevant for some reactions we're going to see. Okay. Any questions about that? Yeah.
So it says that that the lone pairs take up like more space than the atoms. So like why are they harder to look at?
So it turns out that the tools that we have for looking at molecular geometry basically involve like taking whatever molecule we want to look at, sort of usually growing a big single crystal of it and then shining X-ray at it and looking at the scatter patterns as it comes out. And it turns out that atoms are going to scatter the X-rays, but the electron pairs aren't. So pretty much we can just see the atoms, and then we can kind of infer what's going on with the electrons just based on what they do to the atoms. So yeah, there's a lot more to it than that, but that's kind of the simplest explanation. Okay. So any other questions about molecular geometry? Because I think I got a little bit of time to get into the next topic before we end up. So, yeah.
So for the example of bifunctional angles, is there a preference to which one?
Pretty much all of chapter 2 is going to be about that preference and like how we figure it out. So yeah, we'll get there in a bit. This is just kind of introducing it now. So, okay. So I'm going to take a minute and erase the board if you guys want to talk amongst yourselves, I guess. Okay. So we covered Lewis structures last lecture and a bit the lecture before. One other thing that is going to come up here that I probably for future years should shuffle my notes around so that we cover this right after Lewis structures, because cutting back like this is kind of awkward. But resonance structures are one other thing that we need to look at while we're talking about molecular structure. So we've seen that we can use Lewis dot diagrams to figure out the electronic structure and connectivity of a molecule. But sometimes there's more than one valid Lewis dot structure. Even with the same connectivity. So one example that's really common is the nitrate anion. So if we have a nitrogen with 3 oxygens on it and an overall negative charge on the molecule, it turns out the most sensible Lewis dot structure we can put together for the whole thing actually involves having 3 charges on 3 of the atoms. Positive charge on nitrogen here so that it can get a full octet that way, and then negative charges on 2 of the oxygens. And meanwhile, the 3rd oxygen has a double bond. But it turns out there's no particular reason why this oxygen out of here should be the one with the double bond. We could just as easily have drawn this as double bond to the lower left oxygen. And then the other 2 get negative charges. Or we could just as easily have double bonded to the top oxygen and then the other two get negative charges. So all three of these are valid Lewis dot structures for the same set of atoms. You might also be asking, like, couldn't we just rotate it and get the same thing? And the answer is, yeah, this is rotationally symmetric. But we are going to see plenty of cases in the future where that turns out not to be the case, and in those cases, resonance is the only way to interconvert. But this is a nice, simple kind of place to start out. So assuming that every atom is locked in place and we can't twist it around, we can still show three valid Lewis structures for this. So the only thing that's changing between these three forms is not the connectivity. So connectivity doesn't change. Only the electrons are moving from one to another. And specifically, it's the electrons in the lone pairs. Those have moved around, and in the pi bond, we'll cover that later, but in the double bonds. And if we had triple bonds, that would apply here too. Okay, so these are all called resonance forms. And the way that we're going to show the relationship between them is with this special double-headed resonance arrow. And the reason that we need a special arrow for that is because the actual molecule never really exists as any one of these structures individually. It's actually an averaged together version of them. Okay, so the way that we're going to show that is with partial bonds and partial charges. So nitrogen's still in the middle. In all cases, for all the nitrogen-oxygen bonds, we have at least a single bond at all times. So that's going to stay like that. But say we're looking at this nitrogen to the lower right oxygen situation. Here we have a double bond during this form. Then we have a single bond, then we have a single bond. So sometimes it's double, sometimes it's single down here. So we're going to show that as a partial bond. So it's not quite a single, not quite a double, it's somewhere in between. Same over here, same up here. Okay, so the way that we can calculate that is the average nitrogen-oxygen bond order. We just want to straight up average together all three resonance forms that we have. So again, say we're looking at the bottom right NO bond. We've got a double bond, so two bonds, plus a single bond, plus a single bond. 2 plus 1 plus 1 over the three resonance forms that we have gives us an average bond order of 4/3 for the NO bond. So again, somewhere between a single and a double. Okay, we can do the same thing with charges. So the nitrogen, it has a positive charge the whole time. That never changes. So that's going to stay the same in the average together version. The average charge on oxygen, that changes. Okay, I got like 30 seconds left here. So again, say we're looking at the bottom right oxygen. Here it's neutral, so that's zero charge. So 0 plus -1 for this minus charge plus -1 for the minus charge that it has now. Average together across the three resonance forms gives us a -2/3 average charge on oxygen. So we don't have a great way to draw that. We could say -2/3, or we can just be kind of wishy-washy about it and say delta negative here. Okay. So we'll talk a little bit more about this on Friday and then get into atomic orbitals.
an email that I'm still waitlisted for like a recitation, but I still tried to go into my schedule and it said I was enrolled. I'm in the 9 a.m. recitation.
Okay, could you maybe send me an email with your student ID, or if you're free after this class, if you want to come back to my office and we can look at it.
Okay.
It'll take me a few minutes to erase the board, but I can also just meet you over there.
Okay, yeah, I'll try and come back. I have a class in